It's amazing to see you all here. Thank you very much for coming, and I cannot stress enough how it is wonderful to see everybody face to face, of course, and it is amazing to be back on the Black Hat stage. So who we are, just quickly. So my name is Marina Krotofil. Basically, I'm here in the role of the researcher, so I'm specializing on cyber-physical security. Basically, how do we cause physical impact via the means of cyber attacks? I'm not an expert. Will be talk on process control, and I'm not an expert on control engineering, but I'm a hacker, or let's say, in a more intelligent terms, experienced red teamer.
So I'm Rick Derbyshire. I'm a PhD student at Lancaster University. I actually specialize in adversary-centric risk assessment, so I'm looking at the costs and adversary experiences when performing attacks. I occasionally do research on ICS or OT, such as this kind of talk. But yeah, I'm almost finished the PhD, so if anyone's got any jobs to give out, hit me up.
Yes, and of course, also first acknowledgement goes to our contributors to this research. We were not alone here. So we will start with a small introduction into the industrial control system and to the motivation, like why are we giving this talk? So industrial control systems, it's obviously a computer network which typically at minimum consists of two parts. It has a corporate or enterprise network, and then it has industrial network. And even though they have the same PCs, typically they are maintained by engineers because the context in which you maintain in those PCs is so much more important than PC itself. And of course, the computers are basically, when we maintain in PCs, we have a computer science, you apply a computer science knowledge, and then we have, of course, industrial processes, which is the most important part in industrial control systems, which is you apply an engineering knowledge. And then this mixture of all the, different sciences and cultures is, of course, mixing and blending together, creating, of course, a conflict, but it's also creating a little bit of a hurdles for the attacker, because in these systems, the ultimate goal of the attacker is to cause physical impact. It is really frequently misunderstood that once you got access or maybe exploited some vulnerability or got in, that's it. That's the end of basically your exploitation. It's not. It's just the beginning of this journey. After that, you still need to cause your physical damage. And the attacker has to possess this interdisciplinary knowledge in multiple disciplines in order to be able to compile this payload which will achieve desired physical impact. So if you think about this, the attacker has this evil motivation, and then he needs to compile a cyber-physical payload. There are a lot of steps the attacker needs to take to be able to compile that payload. So the attacker is following the cyber-physical attack lifecycle, and do not mix it with the attack lifecycle which describes the intrusion. Here we're describing cyber-physical attack lifecycle, or steps that will take us to the physical damage. And in the past, 7-8 years, I've been researching to death every step or stage of this attack life cycle, including presenting many talks at Black Hat. And a lot of knowledge goes into each stage of this attack life cycle. It's just really a lot. And this is, again, something what is not entirely understood, how much effort goes into compiling final payload. And at some point, we've been presented a research where we took a really very small unit of process, and we took very trivial attack scenario, and just literally getting from this simplistic scenario to finalize this really looking simple attack scripts, it takes a lot of efforts. We barely could manage describing all the steps and efforts in 12 pages of a paper. So the efforts of the attacker are really frequently misunderstood. The most important component in cyber-physical exploitation, after all the reconnaissance and familiarization of your victim, is of course industrial controllers, because at the end they are the final elements which are interacting with field instrumentation, sensors, and valves. And there are different types of industrial controllers. There are controllers as part of the DCS systems. There are RTUs. There is PLCs, which, for example, RTUs and PLCs, right now, becoming a little bit kind of looking the same. And in this talk, we will be focusing on the PLCs. And PLCs are running control logic, which is a key element in the whole ecosystem, because after engineers design the physical process, then you write a program to control it, or basically to manage. It can be written in different languages. It describes all the conditions which happen on the PLC, flags and everything. It's even described basically you even configure how your infrastructure is. For example, if you can see here the Modbus server with IP addresses, everything is in that controller. So control logic is a software or user program which controls or manages physical processes. It defines what should or should not happen when and which sequence and under which conditions. So at the moment, if you would like to analyze the control logic, you would basically, first of all, you need to be an expert in a specific language and a specific vendor. And secondly, you really need to do manual work. So there has been recently one work where if you are able to get your hands over the project file, or basically which is stored on the engineering workstation, that you can perform like offline analysis in a more or less automated way. However, you need to have hold of that project file. In our case, we are considering a scenario where the attacker on the network standing in front of the PLCs and would like to understand what's happening on it. So basically, there have been in the past 2 attacks which involved industrial controllers. There have been Stuxnet and there have been Indestroyer. And they two completely polar examples of precision of cyber-physical attacks. If Stuxnet was laser-sharp surgical precision attack, Indestroyer was literally fire and forget. It's just enumerate any controllable signal on the controller and switch them off. So obviously there is no any intelligence on it. So the approach which we'll be describing in this talk is in the middle, actually. So now let's go to show into the main part, like how can we, which attack surface or which design, let's say, specifics of the industrial controls we're exploiting to actually understand what's happening with the control logic and compile automated cyber-physical payloads. So some preliminaries. So of course, in the OT, everything is standardized. Anything what you need to know, there will be standard about it. So the standard IC 61131 is defining the way how we program in the PLCs. It describes, for example, programming languages, which has 2 types, graphical, text-based, but it also describes which program organizational units we use in the, when compiling when writing level control logic. And there are programs which are the highest level of user program, like it's in, like think of it as a main program when you start programming in the normal world. Then you have functions which are kind of standardized functionalities, but more or less simplistic, like for example, additions or absolute, stop, start, and so on. They don't have own memory, for example. But then there are also function blocks, which is a reusable code, which frequently reoccur and complex functionalities. For example, the PID control, which is one of the main function. And it has own memory, which comes together with the function block. And then there are variable blocks, which actually stored the values of those variables used in the control logic. And that is, for example, if you will try to Google, for example, several terms which we use in this talk, you will have difficulty finding them on the internet. Why? Because, for example, these variable blocks, they are not even explicitly defined in the standard. But that is actually what we are explicitly exploiting in our approach. So it has been 0 days since last research on the Siemens PLC. It's just a favorite target. Siemens just has to accept it. We are no exclusion. So we are just jumping specifically in the specific example, although those principles which are described in the standards are applicable. So this is how, for example, Siemens is referring to those POUs in their ecosystem. So there is organizational blocks, there is I cannot even read function blocks. There is functions and data blocks. So those variables blocks, they call them data blocks. So remember, we will be referring to it a lot. And there is a global data block which stores variables which are accessible throughout, like by every function or function block. And there are local data blocks, as I described, which are previously, which generated together with the function block. And whenever you start, so basically because writing those functions in function blocks is extremely effortful and you require a lot of engineering knowledge. Therefore, your control software is coming already with predefined instruction sets. So those function blocks, they call, for example, the reference in here as instructions. And they already predefined. You basically drag them and use in your program. So they're already written for you. There are also libraries where you can go and can, for example, download even more global libraries. So, for example, this is just very few examples of the function blocks, for example, which you can find. Like there is a PID controller, and as you can see, like depending on which PID control you need, and if you go to the manual, it will be almost 3 pages of exciting reading. They are very, very complex functions. functions. There is here this opportunity to override something, so have a God modus. There is, for example, safety door function from the safety PLC, motion control, drive control, and so on. There is like hundreds of those, and they're all available to you. So this function blocks is something what we will be actually targeting in our approach. Because actually, so this is, like maybe I will recap. So this is the main functionality of the control logic, and this is what we actually want to enumerate to understand what is this PLC is doing, what it is controlling. So the attack objective in general, what the attacker wants to achieve. Of course, enumerate function block, we want to know which function blocks are used. We of course want to extract variables, because then we can, if we extract the variables, we can understand how the process is configured and working. And in general, when we talk about variables, we should probably differentiate between at least like process configuration, infrastructure configuration, because certain variables will be related to how you configure your computational and communication infrastructure and how you configure your like physical process and equipment. And then after you perform the full reconnaissance of your infrastructure, you may wish, of course, to manipulate those variables. And currently, there are absolutely no tools whatsoever to enumerate control logic in an automated way. And this is what we will be offering in this talk. So every function block, as I say, is like each time you deploy a function block, it comes together with a data block. And user is offered with different legitimate means how to actually read the content of the data block. And by processing actually those, what you read from the data block, you actually can identify to which function block it belongs. So, for example, you can query the metadata. There are multiple ways exist how you can basically extract content of the data blocks. There are, for example, you can query the metadata with get block info at the top. And by processing the response, you can actually identify to which function blocks it belongs. There is, for example, something which is called bulk transfer. For example, it's byte upload. You basically upload byte-wise the whole function block. And again, by parsing it and extracting certain information, you can understand which data block it is. But these commands are very rare commands. So they are easily detectable on the network. So obviously, well, that's not very reliable approach. So we were thinking about how can we enumerate these function blocks in a very stealth manner so that basically the modern security controls will not detect them. And for example, there is another way. So read and write are normal commands, legitimate commands on the network, and they will mimic the normal traffic. So you actually can read the contents of the data block byte by byte with the read command. So this is what you see at the bottom. So for example, you see we've read the baud rate and so on. The other piece of information which we need to know is that every variable in the data block, so the memory is organized in a very static and predictable way. And every variable is allocated a very, let's say, predefined number of memory. And for example, if you see at the bottom, we have like a Boolean variable, which is request, I guess. And you can see it's Boolean, so it means it's just 1 bit. But we allocated the whole byte, 2 bytes. So the rest of the memory is just unused. It's just there. And if you just like go to the bottom, you will see that there are a lot of places where, for example, there are definitely more memory allocated than needed. All of that memory is just unused. And this creates actually a unique pattern for each data block that offset and number of empty bits. It's create a unique pattern for each data block, which we actually can then use to understand which data block it is. So this is basically the visualization of what I was just talking about. So if you will basically enumerate for each data block this offset and empty memory, we can like really very reliably enumerate, understand which data block it is. And this is represent this information leakage vulnerability. So this empty memory is what allows us to determine the function block. So this is the pattern. So we basically then this was like previously I've been showing you Modbus serial function block. And if you read byte by byte all of the unused memory, and we know a known location, this is basically create as a unique pattern of that function block. So basically, like if to recap, so our approach to the function block enumeration, first of all, you read byte by byte the content of the data block, and actually a lot of them has a unique length. So you already can identify data block simply by knowing in lengths. Then of course you perform the bitwise matching of 0 patterns at expected offsets, and then you basically repeat these 2 steps until you identify all the function blocks you need. So in a nutshell, our approach is very similar to the rainbow tables which you use to crack passwords. So you basically create your signature set for selected or all which function blocks you know, and you basically it's actually very small because everything what you need to store is just lengths, offsets, and number of empty bits and bytes. That's it. So there are, of course, possible edge cases. There are, of course, collisions. We can avoid them. So even though, like in majority, almost all of them, you can identify it in a unique way in that way. But for example, there are such edge cases, like, for example, counter up and counter down. They are identical. They will have similar lengths and zero pattern. But so if you want to understand which counter it is, you just need to monitor, like, perform 2 times read. Like, for example, for the counter, then you know if it is increasing, then it is counter up. So, of course, and the next thing which you want to do is data block content exfiltration. You want to know to what values those variables set. And you actually do this with a legitimate command read. So the offset for every variable is known because those all those function blocks are available to you in the software. So you know exactly where every variable is located. So you can basically literally do everything with a read command. There is also such case like the long variables. For example, this specific case, for example, PLC can actually email, like, for example, status information or alerts to a certain email address. So it can have email address with a password. So, for example, such long strings are actually stored in the global database, and they are basically then what is stored in the local database is a pointer. So you're extracting the pointer, then you need to reconstruct the pointer. It's very simple construct, plain text. You can easily basically parse it. And then with that pointer, you go to the global database to extract the user name and password. And this is, of course, represents also very interesting information because you immediately can start, like, is there any password reuse? Because typically we use one password for everything. So what we can actually enumerate and exfiltrate? Hundreds and hundreds of standard function blocks, not only from the libraries, from the vendors, but from the consultants company, from the user forums. You can scoop the whole internet and create your comprehensive data set. And then, of course, also exfiltrate variables. So the similar campaign which ever happened in the wild was Havocs in 2013. The only difference is that the attacker was targeting the OPC. So they were exfiltrating all tags to enumerate all the field equipment connected to the industrial controllers. So now, of course, we want to manipulate the content, and here could be a little bit more of edge cases. So it's still possible, but there could be interesting cases. So default variables, we can just immediately overwrite with, manipulate directly in the, like, if the operator did not change them in the data block. If there is, like, variables which are stored in the global database, just because they're coming from there, or basically directly assigned, they will be pushed in the local database every 10 like every cycle. And basically for the attacker, if you want to overwrite it in the local data block, it will be a race condition for you. And basically if you will be fast enough, then this 10 milliseconds will depend, of course, how fast you can generate packets on the network or maybe even queue them. Variables which are, for example, which are signed in via the pointers can be directly manipulated in the global database. So, for example, we can change user like password for the mail. PLC cannot generate alerts send alerts anymore. So, right. So this is basically, yes, so this is an example of how, for example, we were like changing the baud rate for the Modbus. And if you change the Modbus baud rate, for example, it will stop communicate. So there are, of course, also, like, for example, if you not easily manipulate the content, for example, because of the 10-second cycles, there are also alternatives. For example, for the counter, you can directly, instead of, for example, if you want just continuously reset the counter, and the reset function is already set by the programmer, you can, for example, basically write a 0 to the counter, to the output value directly. So it's basically, if you understand how those function blocks works, you will find the alternative, how to achieve what you want, because, again, with read and write commands. So in general, you see, like, this is where you really need to grab your engineer, because like for example, what you see here as an example, it's a block to to integrate drive control from the ABB, and it has 300 variables. Only 26 of them inputs and outputs. So that 270 variables are internal variables for different functionality and calculation. So if you grab an engineer, they will definitely be able to tell you a very smart way which of those variables to manipulate to actually maybe even to achieve some interesting effects. So the approach which we described here is actually applicable to other models of the PLCs which we verified, but it's also applicable, you can enumerate also custom function blocks in the same way. Why? Because they will have the same memory allocation. So what is basically the infection vector and attacker model for this? So of course, the prime victim for this approach is any PLC which is hanging on the internet. If it is hanging on the internet, you can use this approach and directly start enumerating and manipulating. If you're talking about PLC located on the network, then you need to be somewhere on the asset which is allowed to speak to the PLC network. So of course, like this approach is best used if you have a C2 channel, because human in the loop is always better. You can basically analyze the content of the variables and maybe design offline a better damage scenario. But everything we just described is also completely can be a program in an automated payload. It's only that, of course, you will have to put a little bit more effort to design also your decision-making logic when you decide for which value you need to change the variable. I will pass over now to Rick.
Okay. So we've performed reconnaissance on the length and the 0-byte offsets in the data blocks to enumerate the function block. And we can manipulate the variables as well. But there's a crucial thing there. There are 0-byte offsets that are unused in the PLC. How can we use them ourselves? So let's assume, for an example, that an attack has an objective similar to HAVEX, where the goal is kind of large-scale reconnaissance. So they want to enumerate control logic, the function blocks, and exfiltrate that data. So the attacker can use a variety of vectors for delivering the malware. You can look at previous campaigns to see the creative and incredible ways that people have got these pieces of malware physically onto networks. But depending on the network architecture of the operational technology, the malware might not actually be able to talk back to the attacker infrastructure over the internet and deliver the exfiltrated data. This also makes human-assisted process manipulation impossible too, if the attacker can't then communicate with the malware. So the attacker needs to think of a different approach. So let's assume that the diagram down in the bottom right is some distributed architecture such as energy distribution. The HMI that you can see in the leftmost box, that's the thing that the attacker is affected with malware. It can't speak to the internet, and it also can't speak to the back-end infrastructure of the operational technology. Also, compromising, for example, the SCADA server, it's not immediately useful either, because that can't communicate to the HMI in our situation. They are both blocked from talking to one another. However, if the HMI and the SCADA server both have a PLC in common, such as the one highlighted in red, denoted PLC/RTU, they can use that as a proxy to set up command and control. So what we've done is we've created command and control that uses the PLC memory to relay the control and the data traffic. Now, the client and the server enumerate the function blocks on the PLC, and they establish common memory regions that they can use as control and data channels. All this needs is 2 bytes on the PLC. The first byte is for synchronization and control, and you can see the basic example that we did in our proof of concept down on the bottom left. And what this does is allow the client and the server to communicate when they should be talking, when they shouldn't be talking, when they should be reading, for example. Any other bytes that we have access to that are unused on the PLC can then be used for data. And now we can stress here that we can go as granular as using individual bits. However, you've got to be very careful when doing that, because certain variables within certain functions, even if they'll be only using 1 bit in the byte, they'll check the entire byte and they'll throw a very big hissy fit if you start using that. So what our C2 does is it enables the execution of commands at a console or terminal level on the client. And the only thing that restricts us here is the permissions depend on the compromised client privileges. So whatever the client malware has access to, we can then send commands to do. So in our example, the PLC will talk to the SCADA server, which in our example is the C2 server. It will take this over to the HMI, which in our example is a C2 client, and then we can execute certain commands. Now I've got a video here. I have absolutely no idea how well this will execute. Cool. So what we're doing here is we're checking the IP address. You can see on the right that the IP address was 172.21.1.5. Unfortunately, the attacker can't access that. So this is the same situation that we've just described. What the attacker can do, however, is start enumerating function blocks on the PLC. So the PLC is the same IP address apart from the last octet is 101. So we start enumerating function block 100. This will go through byte by byte and read every byte in this data block. This is basically what we've described on the read process throughout to enumerate the function block. So as a little spoiler, this is 323 bytes long. I don't know why we went with this one because I haven't really planned much to say here. So we've basically enumerated every single byte in this data block. And here we can see that this then matches to Modbus serial, but we want to check the bits as well. So these zeros denote that the offsets at 0 are all correct. We've set up the sync on the server, and then we'll set up the sync on the client. This could be automated, but for the proof of concept, we didn't. So now both are synced together. On the client, we can then execute an attack, send the command comes through, executes on the client. Eventually. And there we go. You can applaud now if you want. Thank you, thank you. Okay. Great job, R2, C2, you did it. And for any Star Wars nerds that are getting angry, I know R2 isn't on this, so it doesn't quite fit with the joke, but you got to admit it's a pretty cool picture. Okay, so getting a little bit more serious. What we've described here are a bunch of stealthy techniques through attack techniques and command and control. So we wanted to verify these against prevention and detection best practice security controls. So what we mean here is prevention as firewalls between remote and local network segments, and detection as network monitoring for potentially malicious or anomalous traffic. So we've got 9 use cases here on the right. So T1 and T2 are enumeration via read and write, which are manipulation via write, sorry, which are the stealthy techniques we described before. T3 and T4 are setting up the client and the server for command and control. T5 and T5S are the server sending an nmap command to the client, and the client then performing the nmap top 20 port scan within the field site network. T6 and T7 are the less stealthy get block info and upload techniques. And finally, T8 is a staged interpreter session on the HMI, just kind of as a control variable versus our novel C2. These were all executed as well from untrusted and trusted devices so that we can kind of like get a good idea for compromising a device versus inserting a device on the network that is unknown. And this was all done in our ICS lab. So prevention it largely failed for trusted devices, which was kind of expected. For untrusted devices, most cases we had it correctly prevented. I'm not going to go into any of the cases that didn't. And this is difficult because trusted devices sending legitimate traffic, such as read and write requests, are really difficult to isolate and block. Many industrial firewalls don't really offer any granular traffic filtering, so they only base things on things such as IP address port and maybe high-level protocols such as S7 in certain circumstances. Next generation firewalls do offer more granular traffic filtering rules. However, these are more like rare commands like get, block, info, or upload. Although they do allow you to block read and write, however, this completely stops the functionality of the network in some circumstances, which is, it's too heavy an approach, too heavy-handed. So for the detection of attacks, we use the OT network monitoring solution Clarity CTD. What this does is it creates a baseline of traffic and it detects any deviations from there. And then it also alerts on known malicious traffic or previously unseen devices on the network. Caution needs to be required here when using things such as sending commands over the command and control. Because if the client does things such as mmap, Clarity will definitely pick that up because that's obviously known malicious traffic on the network. So our attack techniques based on read and write commands on trusted devices were only generating events. What this said was baseline deviation, not risky change. As you can see at the table on the bottom, the proposed attack techniques with the intended way of using them, they only generated events. We can acknowledge that this is then creating forensic evidence, and they are kind of being detected, but not really detected as anything particularly malicious. So finally, for the detection and prevention section, I wanted to just come up with some takeaways. So the prevention controls that we tested are really meant as perimeter defense. So because our techniques are often post-exploitation activities inside the perimeter already, they're not really geared up for our techniques. And it's also not really feasible to put a firewall with deep packet inspection in front of each PLC to try and start looking at these in more detail. And in general, even if you could block read and write to specific addresses, it's going to require extensive configuration. It's going to require a lot of precision, and any mistakes in that precision really could pose a risk to operational functionality. And then finally, with detection, the network monitoring tools do offer some opportunity for defense. It would require very granular configuration to alert read-write requests to new addresses within the data blocks. And this then does create a precedent for having too many false positives and create alert investigation fatigue. And that's enough for me, so I'll hand you back over to Marina. Thank you very much.
Thank you, Rick. Well, so what we can conclude from this talk. So quick recap, by exploiting memory allocation and addressing on the modern PLCs, these days PLCs, we develop an approach to enumerate and manipulate function blocks or basically control logic on the PLC. It's applicable to an arbitrary industrial environment, so you can take it and basically you don't need to know anything about your target facility and you will be successful. So basically all of that is done by using stealth techniques which are undetectable because they only use these read and write commands. Fully automated exploit of medium to high targeting precision and can be also used for other purposes, for example, for setting up C2. So when I read all of this, it sounds like, wow, so amazing, so great, so exploit. But in reality, while the impact is really significant, the techniques which we use, they are so simple. They're so simple. It's just like 25, 30 years old in the IT world. So obviously, like the design of the modern PLC is not matching the current, threat landscape. And in general, that this PLC software, and do not mix it with firmware, because currently research is mostly focusing on the firmware, like kind of firmware vulnerabilities, communication stacks. But we're talking here about that PLC software which runs on the PLC. It's largely under-researched threat attack surface. The research which we presented here is not still, let's say, complete, and there is so much more to research. And the only kind of similar line of work which we exists right now is this top 20 secure PLC coding practices. You can check it out. So there is not many device level mitigations for this type of vulnerability. So for example, if you're an asset owner, you of course can start basically set all of your variables, all 300 variables on every function block. You can populate and use memory with random data. You can monitor and use memory. You can perform consistency checks on certain critical variables to make sure that they're not manipulated. But all of this above adds significant overhead to the asset owner or basically PLC programming and maintenance personnel. So it's obviously not scalable. So we really need go to the kind of this protection needs to be on the kind of vendor centric. So and clearly, hopefully it was understood that we really need to start redesigning PLC software, or designs and even the hardware. And the point is that we first need to understand what's going wrong and what is the attack surface in the current PLC, so that we shall take that knowledge and learnings and take it into the new designs. And even like some mitigation opportunities exist on the current PLCs and even in the more modern, like recent model of the PLC, but each of them only offers only partial solution, only in certain conditions or circumstances. It's nothing like you can literally turn it on and you're protected. So you could say almost like we don't have mitigations at the moment. So you probably, like some of you may be thinking like, hey, is there anything will be on GitHub? No. The problem is that this is really something what we don't want this code to land in the hands of the people with unclear intentions, and especially script kiddies who will start tomorrow, will go on Shodan, find all the PLC, start enumerate and manipulate. So in general, our approach is reconstructible with medium effort. So if you know PLCs following this logic, you should be able to create own scripts. And if you do so, please keep it for your consultancy work, for maybe if you want to basically, if you're an engineer and you're asset owner, you can basically check your exposure to this type of threat. And the last note with which we wanted basically to leave you here, and maybe this is also referencing to the our panel which we had yesterday on the vulnerability disclosure. Like at the moment, asset owner seems to be blamed if you have an incident. It's just like you did not secure your asset. But you know, like how can you secure something what if the threat, let's say, attack surface is not even clearly known or understood? So this is representing a completely novel and large attack surface. How can you protect from it if you don't even know about that? So I think vendors really need to start also carry certain types of liabilities for that. And that was it from us. Thank you so much.